Right, this is about improper integrals. Okay, first of all, remember, let's recall it. The definition of a function, definite integral, but that in the definition, the function must be defined everywhere on the interval. Okay, so that's the original definition of this. Yeah, recall that. First of all, f is defined on a closed interval. This is bounded. Okay, closing. Then the integral of the function is defined, which is going to be the limit, okay, of the Riemann sum of xi star and the delta xi. Okay, so that's the definition of the integral. So here delta xi is going to be xi minus the size of the subinterval, and xi star is an arbitrary point. Doesn't matter where it is. Okay. So as long as this limit exists, then you say the function is integrable. Okay. So f is integrable if the limit exists. Okay. So it exists as this delta xi, I from 1 to n. This is the largest subinterval also approaches 0. Okay, there's so many choices for the partition of interval. Okay, but if the size of the subinterval uniformly approaches 0, then the Riemann sum was an arbitrary choice of the points xi star approaches the same number. Then we say the function is integrable, and the integral of the function is going to be the limit. Okay, and the integral of the function. Now, what happens if what happens if the function is not defined a closed interval? Okay, so the first case, the other case is similar. Okay, if the function is defined on the interval, for example, from A to B, okay, and the B could be finite or positive infinity, okay, and this side is open. That means f of B is not defined, or the B is infinity. Okay, for example, B could be 1, could be infinity. Okay, then how do we define this integral? Okay, in this case, it's defined in the following way. Okay, first of all, A, it's a C. Okay, C approaches B from the negative side. Okay, and since C, the function is defined on the closed interval, so that's why this makes sense. Okay, so we know that because here, yeah, the function is defined on the, yeah, okay, note, okay, f is defined on the closed interval, and the C is less than B. Okay, so the above integral, is defined. Okay, so the integral from A to C is defined. Okay, maybe it's infinite. Okay, but it's you know how to define using the Riemann sums. Okay, another I think that's it. And then it could be left in the point. Right. So the second case even worse. If both sides is open, so it's defined on the interval from A to B. Okay, and where A, B finite or infinity. Okay, plus minus infinity. Then then how do we define this? then this should be defined to be a or some number, okay? And that number I can say, let's put a d here, okay? F of x dx plus d of b f of x dx, okay? So so here d is an arbitrary number between a and b, and then this one you can use a right limit. Okay, C approaches A from the right hand side, C to D f of x dx. And this one, and C approaches B from left hand side. This is C. Okay, that's a D. Okay, so that you have to divide the interval into two cases. Okay, let me show you the picture before move on to the next problem. For example, the first case when b is positive finite, the graph could be like that. It's possible, it's impossible to define the function. Okay. Another case is when b is finite. Another case when b is infinity. So it could be, it could be like this. Okay, similar. Okay, so graph goes to infinity here. Okay. Now the second case is both sides of the function is not defined. Okay, then if a b are finite, then it looks like that. Remember the picture for the tangent x, right? And it could be like this, both sides. Okay, and the negative pi over 2 and the positive pi over 2. Okay. See, right? And the function cannot be are not defined at the two endpoints. So how do you define the integral, right? How do you define the integral? Okay, you have to take a two limit, choose an arbitrary point in between them. Okay, another case is it could be like this from this point. Okay, could be like that. Okay, this is like one side is infinity, so it's from from 0 to positive infinity. Okay, this one is from negative pi over 2 to positive pi over 2. The function are not defined at two endpoints. Here's a function are not defined at the 0 and at the infinity, and it goes to infinity, right? So we use that. This is a definition of an indefinite improper integral. We use an integral on the closed interval. Then we take the limit. Okay. So let's take a look at example. Okay. Integral from 0 to 1. Okay. And this one. Okay. Now, what is the geometric meaning of this? Okay. Geometry, yeah. When you compute it, right? So first of all, you say this is going to be c approaches positive infinity, and then from 1 to c and this, right? So right. Okay. All right. Here's when it went. The function like that here, and it's decreasing. Okay. This is a c, right? Yeah, this is c. So the geometry meaning of this integral is the area, okay, under y equals 1 of x between 1 and c is going to be the integral from 1 to c 1 of x squared dx, right? So this is a set. This is a region. The integral represents that region, area of that region. All right. So the limit as c approaches infinity, okay, this can be viewed as the area, okay, of the region This region is unbounded, okay? This region is unbounded, and the y equals 1 over x squared, and the x is between 1 and infinity. So in the unbounded region, you can still talk about the area, okay? We view that as the limit of the area of the bounded region, okay? You cannot say, oh, because it's infinity, you cannot talk about the area. For example, the universe, right? Maybe scientists prove that the universe is unbounded, which means you can always fly to the infinity. You never stop. You never reach the boundary of the universe. But then next question, still scientists can ask, does the universe have a finite volume? The unbounded region in the space, right now we're 1 dimension high. But right, okay, here we only deal with 2 dimensions, right? Unbounded region, okay? Unbounded region does not mean there's no finite volume. The volume could be finite, okay? Okay, because this is getting narrow and narrow, okay? So let's look at, does it have a volume, area, a finite area, okay? This unbounded region goes to infinity, okay? So first of all, you take a look at this integral, okay? And then you will get x to negative dx. So the antiderivative is negative 1 of x, I think, yes, okay? It's easy to figure it out, okay? So the answer will be negative 1 over c minus, it's plus 1, okay? So it's going to be 1. Yeah, it's the same. I should write x to the negative 2 as a power function. So it's 1 over c. Okay, so clearly this approaches 1 as c approaches the path infinity. So that tells you, first of all, the area of that region is always less than 1 and getting close to 1. Okay, so then you conclude that 1 over x squared dx answer is 1. Okay, so that region is a finite area. Okay, now once you do this problem, and you were wondering, is this always true if the function approaches 0? Okay, not that, right? F of x equals 1 of x squared approaches 0 as x approaches infinity. Right? So you may guess, if the value function approaches 0, does this integral finite? Okay? Right? Is the integral finite? Okay. Right? So my question is, if f of x positive and the limit as x approaches infinity equals 0, okay? Is this integral from a to positive infinity? Okay, I know the limit must exist. Is the limit finite? Okay, is the limit finite? Okay, so is this improper integral is actually the limit? Okay, is this limit finite? Okay, let's take a look at an example. Another example. Let's consider this one. Let's consider this. Okay. So first of all, this is going to be the limit as c approaches infinity, and from 1 to c and 1 of x dx. Now, this is by definition, antiderivative of 1 of x is the nature of x. So evaluate to end point. Okay, right? So let's take a look at it. So the limit It's natural log of c minus natural log of 1. Natural log of 1 is 0, so forget the second term. But the limit of natural log of c as c approaches infinity is going to be infinity. Okay, so it's not finite. If you look at the picture, okay, it's still similar, looks like that. But what this difference is this gap. This gap here at the point x, okay, at the point of c. This gap approaches 0. The length of this gap, okay, approaches 0 slower than the one above, in the above example. Okay, so 1 over c is less, no, this is slow, so it's greater than 1 over c squared. Okay, so that means that unbounded region as c approaches infinity close up slower than the previous example, so that includes more area. Okay, so the area of that region, okay, the area of that region is going to be, let's take a look at the area. It's from 1 to infinity, 1 to c, right? 1 over x dx. It's going to be natural log of c. So it's actually a pretty larger number, okay? If c is 100, this is it's going to be, you know, yeah, it is a very large number, okay? So it does not include, so the area as, yeah, it's unbounded, okay? It's different from the previous one. You see, it's the area here, area is going to be integral from 1 to c is actually the 1 minus 1 c. It's always less than 1. It's bounded, okay? And here it's unbounded, okay? So that means the area of the region under that curve from 1 to infinity is going to be infinity, okay? Infinite, okay? It will be infinite, okay? Yeah. Now, after you've done these two problems, you may wondering, can I get a general formula? Okay, instead of, yeah, can I just look at this integral and I can start with a, 1 over xp dx, okay? Here a is some positive number because a cannot be 0. If a is 0, I have a trouble with two ends, okay? Right, because 1 over x to the power p is not defined, okay? And I also assume that p is positive because if p is 0, it's always divergent. If p is negative, okay? So that's a true assumption. Then I'm going to determine the value of p when it's finite, when it's infinite, okay? So we take a look at this integral, right? So x to the negative p dx, okay? So the entire derivative is 1 minus p x to the 1 minus p, right? And evaluate at two endpoints, okay? The first one, yeah, just plug a c. Okay. So it's going to be 1 minus 1p and the c to the 1 minus p minus and a to the 1 minus p. So you don't need to worry about the second term because it's fixed. You only need to worry about this term, okay? Whether this term is going to be finite or not, okay? Okay, so take a look. If p is less than 1, okay, yeah, we have to assume that p is not going to be 1 because we already did the problem, right? So in this case, we assume that p is not going to be 1. Otherwise, I use natural log. So we already did this problem. If p is greater than 0, less than 1, and clearly this approaches positive infinity as c approaches positive infinity. Why? 1 minus p is a positive number. 1 minus p is a positive number. So c to a positive number, okay? As c approaches infinity, if is positive, okay? So using this fact, then you have that, okay? So in that case, this integral, you can simply write this, okay? Okay, that's the first case. The second case, if p is greater than 1. If p is greater than 1, 1 minus p is negative. So this above integral, I'm going to rewrite it in a slightly different way. Look at this. So p is greater than 1. So 1 minus is going to be negative. Oops. My file is gone. All right. If p is greater than 1, I'm going to look at, yeah, this is a from to c, x to the negative p dx. Okay. So I'm going to write in this different form, p greater than 1. And this is going to be a. It's actually is 1 minus p, right? So you can put something like that. And then minus and the c to the negative p minus 1, okay? Something like that, rewrite it. This is a, yeah, originally it's 1 minus p, right? 1 or 1 minus p. So you switch the order because p is greater than 1. This is a positive term, right? Positive, that is also positive, it's minus. Now this term, and clearly this can be 1 over c to the p minus 1. So p minus 1 is positive, so this approaches 0 as c approaches infinity. Okay. So what do and this is this term is subtract a negative term. So so what you see from above, you will see that it's always less than this number, right? Because I subtracted another positive number, and the limit is going to be equal to that number. Right. Of course, that number is finite. Okay. So now we summarize our result. Okay. We summarize our result. We assume that a is positive. Okay. And then integral from a to infinity, x to the minus p dx. Okay. This will be positive infinity if p is less than or equal to 1. If p is greater than 1, and it's finite. Okay. So that means if p is greater than 1, the function closes up, approaches 0 fast enough. Here's a, right? Fast enough. So the gap here is going to be 1 over x to the p. Okay, if p is greater than 1, this gap closes up fast enough to include a finite area. Okay, yeah, to include the finite area. Okay, as x approaches, yeah, if this is put a c here, then we have a c. Okay, so so what does it mean? If p is greater than 1, when the gap here, the length of the gap is 1 over c to the power p. That one approaches 0 fast enough to include finite area. Okay. Then you will have a question, what happens if it's from 0? And then I just put an arbitrary number here. I'm going to take, yeah, I put b here, b is finite. Okay. Now in this case, okay, we assume P is also positive because otherwise this is a trivial case. Okay, only when P is positive, then the graph looks like that. It's going to infinity, and here's a B. Okay, so this is an improper integral. The function is not defined at its origin, right? And we want to determine the variable P such that this is a this is a finite. Okay, from our definition, yeah. So this is going to be the limit of this finite, limit of this integral as C approaches 0 from the positive side, right? That's from the definition. So we take C, and then we consider that since on the left-hand side of this intervals, the height of the graph is getting higher and higher, right? Right, it's getting larger and larger. So we don't know whether this includes a finite area. So do we have the same result? Okay, we probably have a similar result, but I want to tell you it's the opposite way. If P is less than 1, yes, it has finite area. If P is greater than or equal to 1, this has an infinite area. Okay. So how can I see that? Well, let's find the antiderivative, right? Now, I still have to assume P is not going to be 1. So there are 3 cases here because the function is different. Okay, let's assume P is greater than 1. Okay, first case, then we summarize. So Cp and x to the negative p dx, right? The antiderivative is 1 minus p, x to the 1 minus p, and evaluate to endpoints. Now p is greater than 1, so that'll be negative. And b minus p minus. Okay. Since p is greater than 1, so I'm going to switch the order. A negative p minus 1 minus. Okay, so I don't even worry about the second term. What I worry about is the first term. So the first term is this is the power is negative. So actually, you will get something like that. Okay. Now I can put everything in the denominator. Okay, this term is finite. So when C approaches 0, because of the power here, P minus 1 is positive. So clearly, this approaches infinity as C approaches positive from 0 from positive side. Okay. So we solve the case. The second case, P is going to be 1. If P is going to be 1, then x to the negative dx is just natural log of x. That will be negative natural log of v minus natural log of c. But natural log of c approaches negative infinity as c approaches 0. Okay, so that's what this approaches natural log of b plus, actually minus negative infinity. So it's positive infinity. Okay, as c approaches 0 from positive side. So this problem is solved. And p is less than 1, greater than 0. Okay, where's my function? P is less than 1. So I use I'm going to use the original. Okay. So it's going to be 1 minus p, b to the 1 minus p here, 1 minus p, c to the 1 minus p. So 1 minus p is a positive. So clearly, this is a positive, right? This is a positive. Okay. So So this is always less than 1 minus p d to the 1 minus p, right? Because that subtract a positive number here. But it's clearly it approaches n minus 0. So as c approaches 0 from a positive side. Okay, so so the limit is going to be okay. So it's the opposite direction, right? So depend. Right, so right now we have this summary. Okay. If p is less than 1, greater than 0, and it's a finite, and if p is greater than or equal to 1, it's a part infinity. Okay. All right. So that means the integral. Yeah, let's take a look at 2 examples. From 0 to 1, square of x dx. When you see something like that, you know this is already finite. Okay. However, from 1 to infinity, this will be infinite. Okay, it's opposite. And from 0 to 1 and x squared dx, this will be infinity. But this will be finite. Okay. Yeah, let's compare the picture, okay? Let's look at the case y equals 1 over x squared, okay? So that means the gap from here to here, the gap, right? It's going to be 1 over x squared, you know? Okay, that's why it's a finite, okay? But yeah, let's look at this case. So we're trying to find the area of this, but then we view the problem like this. So why 1 over x squared actually is going to be, x is going to be, x is going to be 1 over square of y. So that gap at the point of y, this gap is going to be 1 over square y. So it's no wonder this area, if you look at the region, okay, and the area of this region is unbounded, is infinite because it's 1 over square y. Okay. Okay. So if you calculate the area in a different way, you view this one as a function of a y, okay, and it goes to infinity, right? These 2 pictures pretty similar, okay, but when this one go up vertically, okay, the gap at the point y has a length of 1 over square y. That's why it's similar to that case. That's why it's infinity, okay? So this is the area, yeah. Although the same function, originally the same function looks, right? The same function. But this actually is x equals 1 over square y. That's why. That is why this area is is unbounded. This region is unbounded. The area is infinite. Okay. This is a very good example. It's almost cover all the area, all kind of problems. Now let's take a look at another one. Okay. How about the integral from 0 to 1 natural log of x dx? Okay. Of course, natural log of x is going to be negative. You can put absolute value if you want. Okay. So the picture looks like that. Okay. Does it have a finite? Does it have a finite area? Okay. Okay. So y equals natural log of x. Okay. So x is an e to the y. Okay, so the corresponding picture here, if you draw the graph like that, okay, this is a y-axis, this is a, how can I say? Mhm. Yeah, I use an axis like this. Okay, so the picture looks like that. Okay, this is a picture. It's very just rotate it, okay, rotate. You locate like clockwise. Okay, so the region is this region, right? Here's this region. So I believe that, and this one is x equals e to the y, and the y is negative. Okay, I think it's the gap. The gap here. The gap here actually grows up exponentially. So I think it's a finite. The area is a finite. Okay, it's a negative number. It's a finite. Okay, so how can I do that? So first of all, you find the antiderivative of this function. So this will be x natural of x integral and x times 1 over x dx. So we find that first, okay? Quickly. So now okay. So now this is going to be the limit c approaches 0 from the positive side. Okay, and that is going to be the antiderivative event, right? Okay, so let's plug that one for x and plug c, and that's plus c. Okay, right? So what do we get? Natural log of 1 is 0. Okay, so I end up with c minus 1 minus c natural log of c. So when c approaches 0, c minus 1 approaches negative 1. So what we have to do is about this one. So now I have to find the limit of this. The limit of this, I'm pretty sure it's going to be 0. Okay. You have to use a L'Hopital's rule. That's why we studied L'Hopital's rule before that. Okay, so let's take a look at c approaches 0 from positive side, natural log of c, right? How can I apply the L'Hopital's rule? I can view it as c of 1 over c, okay, right? So this is a infinite type over infinite type. So that's why you can apply L'Hopital's rule. Okay, and here's 1 over c when differential numerator and the differential denominator. You get with negative 1 over c squared. Okay, and after you simplify it, you get negative c, so it's clear it's 0. So this is 0. So the limit is going to be negative 1 as c approaches 0. So my conclusion is it's going to be negative 1. Okay. So the area is 1, and because the functions is below the x-axis, right? Below the x-axis, that's why the area is negative. Okay. So this is the region. The area of this region, okay, is 1, but it's below the axis. That's why the integral is going to be negative. It's going to be negative the area of that region. Now, I'm pretty sure, okay? I'm pretty sure I just showed to you this integral, okay, from negative infinity to 0, e to the y dy, okay? This is also going to be, this is going to be 1. And also, this is going to be 1. Okay. Okay. If I put a negative sign in front of that, then it's going to be, yeah, anyway, this is going to be 1. The reason is I got this from the above picture, but let's redo the problem. Okay, so this is c approaches negative infinity, c 0, e to the y dy, right? And then that be e to the y, c from 0, and e to the 0 minus e to the c, right? Since c approaches in negative infinity, so e to the c approaches 0, so that's e to the 0, which is 1. The reason I got 1, it's not surprise. We're talking about the area, right? This is y equal natural of x, okay? So we're talking about the area of this region, it's gonna be 1. So if I rotate it, okay? So this graph looks like that, right? And that is gonna be e to the x is gonna be the same graph, okay? X is gonna be e to the y, okay? Now if I ask you to evaluate, to find the area of that region, right? Okay. And it's the same region, just rotating the space. Okay, but then this time you have to, the area is going to be, is going to be integral from negative infinity to 0, right? And the e to the y dy. See, that's why it's going to be 1. Okay. Now, if the function is negative, I put a negative sign, then get a negative one, right? Right. It depends how do you view it. Okay. If you just look at the area should be given by this integral. Okay. And this one from 0 from 0 to 1 also gives the area of that region, but that's negative, right? But you have to put a negative sign in front of that, and then you get a positive one. Okay, so there's similarity here, actually. You can get one from another. But let's continue. Okay. All right, so I'm going to take a look at the next one. Negative infinity to positive infinity. All right, so this both sides are infinity, right? Now, how does the graph look like? The graph looks like that. Okay. So the question is, as the geometric meaning of this integral is the area of the region and that curve. Okay, the region is pretty fat in the middle. Then both sides very slim. Okay. Does it have a finite area? My answer is yes. Okay. The reason is when x is sufficient large, this is almost equal to 1 over x squared as x approaches positive negative infinity. And we know the integral of 1 over x squared is finite, okay, over the interval from 1 to infinity. So my guess, okay, this is I know this is finite. So I guess that the integral from negative infinity to positive infinity is finite. Okay, so let's prove it. Verify this. So before you solve the problem, you get some idea what kind of conclusion you're going to get, right? What kind of result you're going to get. So how do we solve this problem? Think about it. All right, so first of all, by definition, now you have to pick up arbitrary point between, okay? So it's a natural idea to pick up a zero, right? Choose a zero as the middle point. And okay, then you evaluate each of the integrals. And it's actually by the symmetry, it's the same. But you can do that, individually, okay? And let's do together. C approaches negative infinity, here C 0. Okay, and this is going to be integral from 0 to C. Okay. Okay. Right. So the entire derivative 1 plus x squared. 1 over 1 plus x squared is arctangent x. This is the correct way to do the problem. Arctangent x. Okay. Then you look at the difference. Arctangent 0 is 0, arctangent C. Okay. And then here's the limit. Again, arctangent C minus arctangent 0. Okay, arctangent 0 is 0. And how about this term? When C approaches negative infinity, okay? When C approaches negative infinity, so it is going to be negative pi over 2, the limit. Okay, and the plus, here's a positive pi over 2. Okay. And minus, so the answer is pi. Now, it's interesting to see that. So what? The area, this unbounded region is going to be pi if the function is 1 over, okay? It's going to be the pi. When x equals 0, this is a 1, right? Now, this is the same as the area of the circle was radius 1, right? The area of the circle was radius 1. This is a circle, right? The circle. Oh, I didn't draw the circle. Let me try again. Get better. All right. So So this circle has the same area. We proved that in mathematics. Have the same area as the region and the graph 1 over 1 plus 1 plus x squared. Okay. Right. It's harder to see without doing calculation. They have the same area. They have the same area. Right? Although the region is unbounded for the under the graph 1 over 1 plus x squared, but then it still includes the same area, okay? As the circle with radius 1. So imagine you collapse the circle and stretch both sides. So you get, it does not change the area. It changes the shape of the graph, right? And so the two sides, and it is two sides goes to infinity, but that gives the same area still. The area remains unchanged. Okay. Now, if the function, okay, then here's some remark. If the function is always positive, okay, and on the interval from a to infinity, then this integral, right? Remember, this is going to be the limit of this finite integral, okay? But this finite integral, there's only two cases here, either positive infinite or finite. Why? Because this increases as c increases. So an increased function, let's call it phi of c, right? A function of c, if it's increasing, then there is only two cases possible. Either it's unbounded, then the limit is going to be infinity, or it's bounded, then it's a finite. Okay. You cannot say the limit does not. So in the generalized sense, the limit always exists. Okay. It's not like other cases, that does not approach the same number, and in generalized sense, infinity, if we consider as a number. Okay. But this, so this always yeah, it's because this is an increasing function. So either goes to infinity or finite. Okay, it has a limit in the generalized sense. Okay. Now there are some functions that does not have a limit. Okay. It does not approach any fixed number or infinity. There are some functions. Okay. Now, how about the integral from 1 to infinity, e to the negative x squared dx? Right? So is it a finite? And how do you see that? Yeah, when it's a finite, it means we said it's convergent, okay? The meaning of this integral is going to be the area that's unbounded region. Okay, y equals e to the negative x squared is going to be 1 over e to the x squared. Okay, it approaches you pretty fast. So I believe that it has a finite area. But how do we show that, right? How do we show that? All I have to do is we have to show this is a bounded, okay? So from 1 to c e to the negative x squared is how do I prove it's bounded? Right? How do I prove it's bounded? So this is e to the, right? Let me draw this. This approaches it very fast. Now, in order to prove it's bounded, I needed to show that maybe it's under another curve, right? If that is easy to understand, then I can prove that's bounded, all right? So what I'm going to do is this is I'm trying to compare those two, okay? So this one is y equals e 1 over e to the x squared. Other one, make it easier, y equals 1 over e to x, because I can handle 1 over e to the x. And which one is larger? I think e to the x squared is less than 1 over e to the x. Okay. Just because x squared is greater than x, as x greater than 1. Okay. So that's why e to the x squared is greater than e to the x. And that's why 1 over e to the square is less than 1 over x. Okay, so great. So that's why this is going to be less than 1 over c e to the negative x dx. Okay. Okay. And then we can evaluate this. Okay, this is going to be antiderivative e to the negative x. Evaluate. Take a look at the difference. All right. Okay, so the answer is this. Okay, so clearly the second number is constant, is positive, so it's less than e. So I get the estimate. So this function is increasing, but this integral, it's increasing as c goes to infinity. Okay, but this function is bounded by this number. Okay, so you conclude that not only you can say it's finite, you can also say that this is less than 1 over e. Okay. All right. So here's our definition. When we say the integral of the, when we say this is okay, if this is a finite, then we say it is convergent. Okay. Otherwise, when it says divergent, okay, here's a function is defined on the interval from A to B, maybe excluding the endpoints. Okay, B could be infinity. Okay. So after the study is proper, let's summarize the theorem. Okay. So if we assume that f of x and g of x, they are continuous on a closed interval from A to infinity. Okay, so you can talk about integrals, and f of x is under g of x for x greater than a. Okay. Then you have this following, so we know that the integral must have this comparison, right? Okay, this side is negative. So if the integral on the right-hand side is finite, then the integral on the left-hand side is also finite. Okay. That's called the sandwich theorem, kind of, between. Okay. So if the conclusion is if the integral of g of x is finite, then the one on the left-hand side is also finite, because we know that it's always greater than or equal to 0. Okay. And this is a useful formula to use it. Okay. All right. So here's a application of this formula. Right. Yeah. For example, right. For example, yeah. For example, just like this. The function looks pretty complicated, right? You don't need to waste time to evaluate this integral. Okay, sometimes it's very difficult. If I put a square of x there, then how do you do that, right? Okay, so this is my f of x. I'm pretty sure this is going to be less than or equal to 1 of x squared. That's a g of x, right? But I know, right? So this is greater than 0. So you see that oops, where is this from? So you know that this is going to be this, right? But you don't need to remember the exact value of this. This actually is a finite according to our first example we discussed. So we conclude that this is the integral of a function like that, okay, is either finite or infinity. So then you conclude this is finite. So it's convergent. It is convergent. Okay, you have to find the right one to compare. Okay, you have to find the right one to compare. Okay. Let's try another problem to compare it. Okay. This is the integral from 0 to 1. And I have a sine x and an x x squared dx, for example. All right, take a look at this function. Okay, this function is defined on interval from 0 to 1, closed. Okay, so there's a trouble point here, end point. So this is the improper integral. By definition, right, this is going to be integral from c to 1 sine x dx, okay? Okay, right? So how do you show this is a finite or divergent? Are you able to evaluate this integral? Yes, it's very complicated. So we have to use a comparison. All right, sine x. Yeah, probably have to find out that sine x has kind of you know, it's good. It's actually almost equal to x. Okay, as x approaches 0. Remember, right? So sine x over x squared is almost equal to 1 over x because x over x squared. But we know that the integral from 0 to infinity, from 0 to 1, this is a divergent. Okay, we already know that, right? We call the example we discussed. So my conjecture, right? Okay, right? But this is just the conjecture. Okay, we haven't proved it. So what I want to do is I want to, in order to prove this is infinite, right? So I have to show something like that. Sine x over x squared, right, should be greater than something, a number, okay, positive number, x, then this side is positive, right? So then, right, and if this is infinity, then the other one must be infinity, right? So you have to get a lower bound for sine x. Right? Do we have a lower bound for sine x? The answer is yes. I guess, I know sine x is less than x, but how can I get a lower bound for x between 1 and 0? Right? How can I get that? Well, I'm pretty sure this is going to be, it's easy to check, and maybe I cannot have I can x there, maybe have a 10x, okay, something like that, okay, okay. Right? But you have to prove this was it's true for x between 1 and 1. Let's put aside, okay, and if you're not sure, then put the 100, okay. so that's why that is why sine x over x squared is greater than or equal to 1 over 100x over x squared, and that's just equal to 100x, right, for x between 1 and 0. So that forces, right, 0 to 1, 100x dx, that's infinity. And the other side also, yeah, it's from 0 to 1, sine x, x squared dx. That's why it's infinity. So it's divergent, okay? Divergent. So the only problem is, how do I know this is true? Well, you better guess, okay? But in order to prove that this is always less than sine x, you have to look at the function f of x, okay? You take the difference, right? You take the difference, like 100 x minus sine x. And you want to prove this is a negative, right? Or you switch the order, doesn't matter, right? So it's f of 0 is 0, right? Okay. Okay. So f of 1, f prime x is going to be 100 minus cosine x. Okay, 100 cosine x. And that is going to be, negative, okay, because for x between 1 and 0, okay, why? Because cosine 0 is 1. Well, it's a little bit different. Okay, y cosine 1, if cosine 1 is, if cosine 1 is going to be what? It's pretty large number, okay? Now, if you're not sure, then I change 100 to cosine 1, okay? Then it's always negative, okay? So, but cosine 1 is a positive number, but cosine 1 is indeed larger than 100, okay? If you're not sure, then but it's positive. Cosine 1 is positive. Okay, so you are not sure, then you change 1 over 100 to cosine 1, right? Cosine 1 x. After you differentiate, this is yeah, right? And this is going to be less than cosine 1 minus cosine 1. Right. Right. So that's going to be 0. So that's everywhere it's positive. Everywhere, you know, it's negative. Once it's negative, then think about this function. This function is decreasing. This function is decreasing, and it's 0 here. It's decreasing. So f of x is always less than f of 0 for x between 0 and 1. Okay. Okay. This is 0. Okay. That's why cosine 1x is less than sine x. Okay. 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 That's enough, you know. Yeah. If we can use a calculator to estimate cosine 1, then you replace by other numbers. Okay. So that's going to be 0. Okay. Greater than 0. So anyway, you have this identity, then cosine 1x over x squared is less than sine x over x squared, and this side is just equal to cosine 1 over x, and cosine 1 is constant, you know. Okay, then you stop here. Okay, you are done with the problem. All right, yeah, then you integrate. Cosine 1 is positive. That's why it's going to be, this is going to be positive infinity. It's less than or equal to. Okay, so that forces the one on the right hand side is the positive. It's the divergent. Okay, divergent. So what I'm trying to do here, I'm not going to evaluate the integral sine x over x squared. I just use a comparison to make sure this is divergent, to prove this is divergent. Okay. I'm going to stop it here.